Hi, this is Dr. Habib Ahmed, and today I'm going to show you the Silvaco TCAD simulation of gallium nitride based high power PIN diodes. Before running the simulations, I want to tell you about the significance and applications of high power gallium nitride based PIN diodes. So here are a few slides from my final defense presentation of my PhD. Gallium nitride has some properties which makes it a beautiful choice for high power PIN diodes for high power applications. First of all, it has a wide energy band gap of 3.4 electron volts. Secondly, it has a high critical electric field of approximately 3 megavolts per centimeter, which is approximately 10 times higher as compared to that of silicon. Third, it has high electron mobility and saturation velocity. The saturation velocity of gallium nitride is approximately 3 into 10 to the power of 7 centimeter per second. These properties are crucial. There are a couple of figures of merit. One is called Baliga's figure of merit and the second is called Johnson's figure of merit. These are the figures of merits for high power devices. Baliga's figure of merit is more relevant to PIN diodes and the Johnson's figure of merit is more relevant to transistors. In Baliga's figure of merit, we mostly care about it mostly depends on the reverse breakdown voltage and on the on resistance of the device. It also depends on the critical electric field. If it depends on the breakdown, it depends on the critical electric field of the material. For transistors, the Johnson's figure of merit depends on the critical electric field and on the saturation velocity. So here is a comparison of gallium nitride versus other semiconductor technologies in terms of Baliga's figure of merit and also in terms of Johnson's figure of merit. And as you can see that these two figures of merit for gallium nitride are way higher as compared to silicon carbide, indium phosphide, gallium arsenide and silicon, which making it an optimal choice for high power PIN diodes. So the reverse breakdown characteristics of high power devices play a critical role in ensuring their reliable operation, protecting them against over voltage ratings, minimizing power losses, and enabling efficient performance in various high power applications. For example, voltage blocking capability, reliability and robustness, protection against over voltage, leakage, current control, design flexibility. Why is design flexibility important? Because understanding the reverse breakdown characteristics allows engineers to design high power devices with specific voltage ratings and leakage current requirements tailored to the application's needs. And this flexibility actually enables the development of customized solutions optimized for different voltage and power levels. High power gallium nitride PIN diodes find applications in various fields due to their unique properties such as high breakdown voltage and high switching speeds. Gallium nitride PIN diodes play a crucial role in various high power and high frequency applications where efficiency, speed and reliability are essential requirements. Some common applications of gallium nitride high power PIN diodes are radio frequency power amplifiers for wireless communications like radar, satellite communication, cellular communication, etc. Because gallium nitride can handle high frequencies and power levels efficiently. Secondly, these PIN diodes are suitable for power supplies and converters. Their high power handling capability and fast switching speeds improve the efficiency and performance of these systems. Third, they can be used in pulse power systems for generating short pulses of high power, which are used in applications such as laser drivers, medical equipment, and particle accelerators. Fourth, they can be used in switching devices where fast switching and high power handling are required, such as in power electronics, electric grid systems, and military applications. Fifth, they can be used in high frequency circuits for signal modulation, frequency mixing, impedance matchings, in applications like radio frequency identification, microwave communication, and aerospace applications. Sixth, gallium nitride PIN diodes are employed in medical devices such as MRI machines, X-ray generators, and radio frequency ablation systems due to their ability to handle high power levels and fast switching speeds. 7. Gallium nitride PIN diodes are utilized in laser diode drivers for controlling the output of laser diodes in applications such as laser cutting, welding, and medical lasers. 8. Gallium nitride PIN diodes find applications in high power microwave systems for generating, amplifying, and controlling microwave signals in defense, telecommunications, and research applications. So it has a lot of applications. Now with that background information, now we are going to focus on the Silvaco TCAD code for gallium nitride based high power PIN diodes. So basically I have worked on multiple structures. For example, here is my p-type layer. This layer is the I layer, and this layer over here is the n-type layer, and I'm going to give a detailed description about it as well. But as for now, so I worked on multiple structures, and I varied the I layer thickness in the range of 0.5 to 5 micrometers. Like I run the simulation for 0.5, 1, 2, and 5 micrometers. And I looked at the forward biased, but more importantly, I'm interested in the reverse breakdown performance of the gallium nitride based high power PIN diodes. Before running the simulation, I want to show you a paper. We published this paper in May 2022, and in this paper I performed some initial modeling work where I calculated the reverse breakdown voltage for gallium nitride and the on resistance for gallium nitride versus doping concentration and the I layer thickness. So as you can see over here that the breakdown voltage depends on these two parameters, the doping concentration and on the depletion layer thickness. Inside the code that I'm going to show you, I have set the carrier concentration of the I layer to 10 to the power of 16 per centimeter cube. So if you focus on the red curve, you may be able to figure out that the capability or the depletion rate capability of this I layer for the doping of 10 to the power of 16 per centimeter cube is approximately 20-25 micrometers, which means that we can utilize the potential of the I layer up to 25 micrometers at this doping concentration. But beyond 25 micrometers, it's going to the reverse breakdown is not going to increase. So our I layer thicknesses are well within this range. Let me zoom in on this. I have set the I layer thickness to 0.5. In fact, first I have simulated a gallium nitride PN junction diode, And then I've run different codes for eye layer thicknesses of 0.5, 1 micrometers, 2 micrometers, and 5 micrometers in the Silvaco TCAD. And then I'm going to show you the results for the Silvaco TCAD results for that. These plots, I've done that in this paper using MATLAB, using some modeling and physics of impact ionization in order to determine the reverse breakdown and the on resistance of gallium nitride based PIN diodes. And in this paper, we also performed some experimental growths of PIN diodes. But as for now, for this lecture, I'm going to focus on the Silvaco TCAD simulation part. I've copied this code in a Word document. So in this code, I'm going to show you the Silvaco TCAD simulation for an eye layer thickness of 1 micrometers. And it's going to take a lot of time to run the simulation for each and every individual eye layer thickness. So I will already perform the simulations for the remaining thicknesses as well. So once I show you the simulation of this structure with an eye layer thickness of 1 micrometers, then I'm just going to jump straight to the results of the other eye layer thicknesses based devices as well. In this code, I have made the structure in Athena, and then I performed the IV characteristics of the device in Atlas. So we start with Go Athena. My meshing is running from 0 to 5 micrometers in the X direction and from 0 to 1 micrometer in the Y direction. So if you look at this structure, initially it's running from 0 to 1 micrometers in the Y direction. In the X direction, you may say that it's running from 0 to 10 micrometers. But in fact, what I'm going to do is, initially I'm just going to create half of this structure, like the left side to the left of the 5 micrometers. And then with a simple mirror command, I'm going to replicate it to the right as well to build the entire structure. The first thing I need to do in Athena is for doping is to define the dopant types. So here I have defined silicon as a donor and magnesium as an acceptor for these PIN diodes. Then I have set the silicon doping of this initial layer to 1 into 10 to the power of 19 per centimeter cube. So so this initially basically is a 1 micrometer N-type layer. As you can see here, it's running from 0 to 1 micrometer with a carrier concentration of 1 into 10 to the power of 19 per centimeter cube. Subsequently, I have deposited a 1 micrometer gallium nitride layer on top of it with an electron concentration of 1 into 10 to the power of 16 per centimeter cube, which is the I layer. This layer over here, I have set it as an I layer, and I've set the doping of this to 1 into 10 to the power of 16 per centimeter cube electron concentration, followed by 0.5 micrometers magnesium doped gallium nitride layer with a whole concentration of 1 into 10 to the power of 18 per centimeter cube. So this layer over here has a thickness of 0.5 micrometers. Then I deposited a 0.2 micrometers platinum layer, and then I deposited 0.2 micrometers oxide layer on top of that. I etched the oxide to the left of 2 micrometers, then I etched platinum to the left of 2 micrometers, then I etched the entire oxide, and then I deposited 0.3 micrometers oxide, and I etched the oxide to the right of 4 micrometers. So this sequence of commands actually resulted in, if you focus, so if I zoom in on this, okay, so if you focus to the left of 5 micrometers, so you can say it resulted, this layer is platinum, this layer over here is the oxide layer, and you're gonna see it better. Like if I go to display and I disable the dopings, you can see it better. Now this is the platinum layer and this is the oxide layer, and as for now focus to the left of 5 micrometers, so basically we have completed half of the structure so far. Then I have introduced this command struct mirror right, which is going to mirror the structure to the right. So now my structure is running from 0 to 10 micrometers in the x direction. After that, I've assigned platinum as an anode at x is equal to 5 and y is equal to minus 1.5 coordinates, and I've set the back side of the structure as cathode. Then I save the structure, and then I start working in Atlas module of Silvaco TCAD. So I input this already saved structure, I imported, and then I introduced models for running the simulation, for example bipolar. This one is a crucial command for smoothly running the breakdown performance of different devices. It's a band-to-band tunneling. Then I've introduced other commands, for example recombination, band gap narrowing, concentration dependent mobility, field dependent mobility, etc. I want to look at some output parameters, the energy band diagram, and some other parameters. I also want to look at the current flow lines. So I've introduced these commands. I have introduced a method for the numerical solution of this device. The method is Newton. This command over here is also crucial for simulating the breakdown performance of devices. So basically what happens is that under high electric fields, under high voltages, we have high electric field as well. So the carriers, they gain enough kinetic energy, so much so that they can knock off secondary electrons from other atoms as well. And this process builds up, resulting in an avalanche process leading to high current. So I have included the Silberher model of impact ionization in order to perform the breakdown performance of this device. Then I have saved the structure under thermal equilibrium. Then I created a log file with this name in order to perform the forward bias IV characteristics of this device structure. My voltage is running from 0 to 5 volts with steps of 0.1 up to 2.8 volts and from 2.8 to 5 with a step of 0.05 volts. And then I plot the forward bias IV characteristics of this structure. Then I log off this file so that it does not mess up with my upcoming log file. I perform curve tracing in order to determine the breakdown point. So here I assume that 1 milliamps under reverse bias is my breakdown point. So I'm actually running the simulation until I find that 1 milliamps current point. And for that purpose, initially I've set the voltage to 0.01 volts, and every subsequent step is 1.02 times the previous step. So it's going to keep running until it finds that point where my current is 1 milliamps. Then I save the log file and I plot the log file, and I save the structure under reverse bias as well. So let me check one particular point. I want to look at the structure as well under reverse bias, which is not initially part of this Word file, but I have definitely included it into the Silvaco TCAD deck build environment. So at this point I'm going to run the simulation. I'm going to close the previous 20 plot. Here is my structure under thermal equilibrium. If I go to display, you can see the meshing. Then we can click on contacts and hit apply. So here is my anode, and this point over here, the back side of this structure is cathode. Similarly, we can look at the doping profile. So I click on this icon, which is contours. Then I go to define contours, and instead of absolute net doping, I want to click on net doping so that I can see which regions are p type and which regions are n type. So here is the distribution of the carriers in different regions. This region over here, as you can see from the color chart, is n type with a doping concentration of 10 to the power of 19 per centimeter cube. Similarly, this region is also n type, as you can see from the color chart, and it has a doping concentration of 10 to the power of 16. It's not obvious from here, but I'm going to show you how to exactly determine it. This region over here is p type with a doping concentration of 1 into 10 to the power of 18 per centimeter cube. If you want to find it for sure, you can go to tools, cut lines, and draw a cut line across the structure. And now you can see that our dopings are 10 to the power of 18, 10 to the power of 16, and 10 to the power of 19 per centimeter cube for these three regions. I'm also interested in looking at the energy band diagram. I love energy band diagrams. I believe that if you are good at energy band gap engineering, you can almost design any kind of device. So then I go to display, and instead of net doping, I want to click EC of T, EV of T, hole Wave and electron quasi-Fermi level. Here is my energy band diagram. As you can see on the left side, we have p-type layer, then we have this low doped, or we can call it intrinsic layer, and to the right of that we have the n-type layer. Okay, the rest of the simulation is also run. This is the IV characteristic under forward bias. So I go to display, and I want to see anode current versus anode voltage. The turn-on point under forward bias is approximately 3.4 volts. Similarly, here is the reverse bias IV characteristic of this structure, which we performed using curve tracing. So I want to look at cathode current versus cathode voltage, and as you can see that the current drastically starts increasing around this point, and we have assumed that 1 milliamps is our breakdown point. At this point my voltage is approximately 275 volts. So I assume that 275 volts is the breakdown point for this gallium nitride PIN diode with an I layer thickness of 1 micrometers. Also, I want to compare it with the modeling that I performed in my paper. So for 1 micrometer I layer thickness, which would be this point, if you focus on the blue curve, which corresponds to the breakdown voltage, at 1 micrometer the corresponding breakdown voltage is it's above 200 volts, close to 250 or 275. We can draw a line over here, but it pretty much aligns with the previous modeling that I performed in MATLAB in my paper. So there is an agreement between these results. I also want to show you something else. So here is the gallium nitride PIN diode under reverse bias. And if I go to display, we can look at several parameters over here in this structure. Like for example, we can look at the current flow lines. So here are the current flow lines at 275 volts for this structure. Similarly, more importantly, we can look at the electric field across the entire device at this reverse breakdown voltage point. For that purpose, we go to contours and I want to find electric field over here. Here is the electric field. Similarly, as I already told you that the critical electric field of gallium nitride is approximately 3 into 10 to the power of 6 volt per centimeter, or you can say 3 megavolts per centimeter. So I fix this value to 3 10 to the power of 6 volt per centimeter. You can see the unit over here. Then I hit apply and click OK. Here is the reference color chart, and from this reference color chart you can see that my critical electric field is distributed around here in that region, which means that my device is going to break down in this region for the gallium nitride PIN diode. So it's a crucial thing that you can look at using Silvaco TCAD simulation. You actually know where exactly your breakdown is going to occur. So these were the results for 1 micrometer, but as I already told you, I also performed the simulations for a gallium nitride PN diode, and as you can see for gallium nitride PN diode, the breakdown point is approximately 35 volts. For 0.5 micrometer, the breakdown is close to 150 volts. For 1 micrometer, it's around 275 volts. For 2 micrometers, it's close to 500 volts. And for 5 micrometers, it's close to 1000 volts. So similarly, you can perform the simulation of quasi-vertical devices by introducing impurities, etc. as well. So here is how we perform the Silvaco TCAD simulation of gallium nitride based PIN diodes for high power and high frequency applications. Take care, and I will talk to you next time. Adios.